I'd like to welcome my colleague, Professor Mikhail Lukin, Misha, to our Einstein Revolution course. And maybe I just begin by asking you how you became a quantum technologist. I mean, how did you come to this area of work?
So as a student, I was both mystified and fascinated by quantum mechanics. And I think it's fair to say that, if you were not confused by quantum mechanics when you learn it, you never completely understood it. And for me, this path took me all the way from Russia to Texas, and eventually here to Cambridge. But sort of more importantly, what I was really fascinated by is by the ability of modern experimental technology to really probe these deep fundamental mysteries of quantum mechanics, to really, for example, prepare the superposition states of two objects in different states at once, to create entangled states, to probe these non-local properties of the entangled states. And these are the fundamental principles which are behind what we now call the second quantum revolution. The idea of using controlled quantum systems to explore both new science and perhaps develop new applications.
Can you describe in sort of basic terms what, for quantum computation, you're after in the lab?
So in order to make a quantum computer, even a small one, you need to have several important ingredients. First of all, you need to be able to store information in these quantum mechanical superpositions. And one of the key challenges there is that generically the quantum superpositions are extremely fragile. So we already talked about the example of this, Schrödinger cat states. There are not too many cats of this kind running around, right? And there is a good reason for that. Whenever a quantum system is exposed to interaction with surrounding environment, these quantum superposition states often collapse. So the environment essentially makes as a meter, which kind of measures, and collapses a state.
Then you either have a dead cat or a live cat.
Live cat, exactly. And that's, of course, this is not acceptable if you really want to build a quantum machine. And so a big part of our efforts now is to really try to create quantum bits which can have superposition states which are long-lived. And a lot of strides have been made actually over the last 2 decades along this direction. So as a matter of fact, we can now store information in just individual atoms which are basically in a solid object, under ambient conditions at room temperature, and these objects can keep quantum superposition states for macroscopic times, for several seconds.
What kind of atoms are you using? What kinds of materials?
So these are typically, so this specific example which I gave involved essentially a diamond crystal, and diamond is of course a unique material known for its, hardness and all sorts of other unique properties. But actually it turns out that the diamond is also a unique host for kind of atom-like impurities. So if you start with the diamond sample, which is extremely pristine, extremely pure, and implant a single nitrogen atom inside, this creates a defect in diamond lattice, and it turns out that we can actually, by using lasers, we can first of all observe this single atom one at a time, and then manipulate its electronic state, prepare the state where this atom is in several states simultaneously, prepare these superpositions, and then later on read out the state of this atom also by using laser light. Depending on its internal state, this impurity is either darker or brighter.
So you can tell that it's kept in its superposition state for several seconds.
Exactly, and this, through this kind of techniques, and through the, manipulation and massaging this, state of this atom, we actually can encode the information, keep it there for a, reasonable time, and then decode it. So that gives you a fundamental building block, this so-called quantum bit, which you could then use as a starting point to build more and more complex systems.
It's like it's the analog in a classical computer of a little switch that's on or off, 1 or 0.
Exactly.
Only now we have something that's both in this state and that state, and we can keep it that way and eventually manipulate it and combine it with other such bits to build a computer. That's the hope.
That's the idea. But actually, interestingly, even when these quantum bits can be created in isolation, one at a time, there might be already some interesting potential applications of such a system. And one of these applications is actually the concept which really started out this field, and this concept is known as quantum money. So it was actually proposed by Steven Wiesner, who was actually a graduate student in late 60s in Columbia, and he wrote a paper as a graduate student, and he couldn't publish it. People thought that it's completely crazy, and basically it came out maybe only 10 years later. But this was a really visionary idea, which is now the basis for other fields. Basically the idea here is that you can use this quantum superposition for secure encryption. So, for example, if you start with one of this quantum bit memory, you can encode superposition. You can encode classical bit of information, basically using the different bases, using, if you want, the different orientations of the quantum bit.
So let's say we have, let's use a simple system. So if an electron, say, is spinning, it makes a little magnet, say, pointing this way. And if it's spinning the other way, it's pointing that way.
Exactly.
So in a quantum state, the electron can either, the magnetic axis, the spin is considered to be up or down if we measure it along this axis. But if we were to measure it along a different axis, then we would get other results.
Yeah, so exactly. So basically this is an excellent analogy, and this basically illustrates that what you can do, you can, for example, encode a bit of information such that the spinning top would point up or down, or instead you can encode a bit of information in a basis where it either points left or right. So this is a very simple concept, and once you encoded the information in these two bases, if you know the basis, you can go and make a measurement and find out, which bit of information you encoded.
So if I have an electron pair, and one of them is spinning up and one of them is spinning down, and I send one to you, we can keep this secure like that.
Exactly.
But if some spy or thief came in and they didn't know that we were using this up and down axis, and they tried to use the axis going horizontally, it would wreck the information.
Exactly, it would wreck the information, but the spy or thief, moreover, will not be able to find out what the original encoded information was. What basically he or she will get is a random outcome of the measurement.
So this becomes a secure way of using quantum mechanics for me, if you're the bank, for me to send information about my credit card or something else.
Or even encode the information. So if you had a credit card where instead of basically magnetic stripe, you would have this kind of quantum magnets, right? Then as a bank, I could basically encode your secret code in such a way that no one, even you, would not be able to actually copy this code. But I, as a bank, I would be able to verify this code is really, the one that I have created and issued.
what it does, it would specify that we're measuring along this axis, or we're measuring along this axis, or this
exactly.
axis.
Yeah, the encoder, knows this information, and then when you, try to use the credit card, it can make the measurement in the right basis set, and then, verify that the result which was measured is precisely the result which was encoded. However, if someone else tried to do it, to kind of make a measurement in order to copy this information, he or she would fail. So that's actually the basis of one fundamental result in quantum mechanics, which is called no-cloning theorem. So the unknown quantum state, the quantum state which you encoded in a superposition of two different states, an arbitrary superposition, cannot be cloned, right? And so that's the basis, fundamentally, behind this concept of quantum money. This is also the basis for other encryption ideas like quantum cryptography. But basically, what this shows already, even with just manipulating of single quantum bits, if we could store them for kind of macroscopically a long time, we could create some unique capabilities which, in the classical world are totally unimaginable.
So if there was a big organization that was reading messages, even they, if they didn't know which axis to measure, would get random results and wouldn't have the information.
So that is, of course, now this is, kind of a very, popular topic for discussion. But, this is a basis for a technology which is called quantum cryptography. So at least one version of this quantum cryptography is in some remarkable way connected to one of the Einstein's insights into basically the fundamental issues of quantum mechanics. So in particular, one of the version of the quantum cryptography makes use of Bell's theorem. Mm-hmm. And the idea basically is the following. Suppose now, instead of one quantum bit, you have two. And suppose that somehow you can create the state of this two quantum bit, the superposition state of these two quantum bits, which is entangled. So if there are two parties, Alice and Bob, who want to communicate, each possess a part of this entangled state, what they can do is they just can make independent measurement of this entangled state along certain chosen orientation, basis orientation. And these entangled states or entangled superpositions, they have some unique properties, such as, for example, quantum correlations. So if the Alice measures, for example, along this so-called up-down basis, right, when the spin points up and down, and Bob does the same, then the results, for a certain entangled state will be always anti-correlated.
Right, so if one's up, the other's down. If one's down, the other's up.
Exactly. But of course, the results will be always random, right? So what this means is that by doing that, they will then share a secret key that no one else can possess. Moreover, in the cases when they do not measure in the identical basis, they could also use these results. And what they can do with that is basically use them to verify that a channel is secure. For instance, they can use these results to test Bell's inequalities. And once you see that this entangled states, entangled pairs that they share violate Bell's inequalities, the properties of these entangled states are such that basically they essentially guarantee that only these two parties are in possession of these unique correlations, which results in secret key. So what it means is that by violating Bell's inequalities, they could essentially guarantee that no one else could be listening, that no one else has an access to these quantum correlations. And so that is the basis for quantum cryptography. And in fact, this quantum cryptography is a rapidly developing field. where you could already, buy some relatively simple quantum encryption systems.
All of these things that you're describing, using correlations that are set up in a superposition and sending one, keeping one, to do banking in a distant way and reveal if any thief is coming in to try to steal the information, or have something that's in two different states at the same time in order to be able to have quantum parallel computing to vastly increase our speed. These are fragile systems typically, and as soon as they come into contact with something classical or with ordinary kinds of things, suddenly it's like opening Schrödinger's box and finding the cat, either alive or dead, but not in a superposition. So we lose the special, bizarre qualities of the quantum world very easily. It's that fragility. But that's something you've been thinking a lot about how do you keep the quantum effects but not make it too easily destroyed?
So that's, of course, the fundamental challenge in terms of realization of all of these ideas. And one can make, once again, going to Schrödinger's cat analogy, is that, we don't see much of this, cats walking around. And the reason is that if you create this, especially a complex quantum superposition state, any tiny perturbation which affects this state often collapses the state.
Collapses it into be a classical state.
Exactly, into a classical, into one either cat alive or cat dead. And that's of course a problem which have been realized early on, and there are basically several ways how this problem is being addressed. One approach is to try to isolate the systems as much as possible. So, for example, some of the leading candidates for realization of a scalable quantum computer are cold trapped atoms and ions, where essentially you have vacuum tubes, and these atoms are suspended in a vacuum, right? So they really, are isolated from everything. What
so you have
is
electric
going
and
on.
magnetic fields that
Exactly.
hold it in.
And then what you typically do also, you sometimes can build a cavity around it, so that can be also isolated from radiation, external radiation. And generally, these are the systems which at the moment are kind of viewed as perhaps among the most promising starting points for realizing quantum computers. But then of course there might be other ways how to create this isolation, and in the example which I gave before already, we have succeeded in creating a quantum bit which is actually in a room temperature solid under the ambient conditions, and the key there was to encode the information into a nuclear spin degree of freedom.
So you have a nitrogen nucleus located inside a diamond.
Exactly.
At room temperature, and you're coding how the nucleus of nitrogen is spinning.
Exactly. And these nuclear degrees of freedom are actually quite special, because basically the only way how they interact with environment are through their tiny magnetic moments, and that makes them extremely robust. So that is, for example, also the basis behind magnetic resonance imaging, where you look at many nuclei at the same time, and you probe essentially their evolution, you probe their precession. And their precession gives rise to the information about their environment, but this precession can last for a relatively long time, even in a living systems. So one maybe last thing that I would like to mention is that there is now also some fascinating direction involving the use of topology to protect quantum information. And the idea here is to really create some new states of matter in which the information, quantum information, is encoded into basically topological phases, which are not sensitive to local changes in your system, but only sensitive to changes in topology.
So something like a hole in a system.
Exactly. So if you have so basically you can have two quantum states. One is, which one can be thought, having topology like this cup, for example, right? Where you have some opening, and another one is a ball, right? So if you create a superposition state of these two objects, in a certain system, it turns out that this state, under some conditions, could be extremely robust.
The state that's
the
a
superposition of these two,
something with a hole and something without a hole.
Could be extremely robust, and the reason is that basically, in order to convert one to another, you really have to change the topology of the system. So, once again, these are extremely fascinating ideas. Only now we are starting to approach to probing them in the lab, but that really shows the interplay between basically, creating new quantum materials which possess this kind of systems, some fundamental quantum mechanics involving superposition states, and also information science. So, this is...
What I find so fascinating about this is that in order to do engineering, or what we hope will be one day a technology of these things, we have to go even deeper into the quantum world and say, how are we going to keep this quantum system, this fragile quantum system, from collapsing into just ordinary classical objects? And what you've been telling us is that we'll use some very strange quantum features to try to keep that information in its quantum state. For example, a state that went back and forth between being something with a hole and something without a hole. Or by using a superposition, say, of one particle spinning up and one down, so that if one of them got wrecked, the other was still there. A little like analogy might be our DNA works by redundancy. If a cosmic ray comes in and wrecks one strand of our DNA, well, it's a double helix, so we're still good to keep from getting cancer. So you're constantly looking at the strange quantum aspects of the world, superposition and entanglement, as ways of keeping the quantum world intact against all intrusions by the classical world, so that we can use that quantum world to transmit, manipulate, calculate using this quantum revolution.
Yeah.
Great.